Welcome to this session about data storage, sharing, and transfer. This session will try to share some tools, some tricks, about storage, transfer, and sharing of scientific data. And I will start first with storage. It will not be a comprehensive tutorial on all the subjects that I will show you, but rather a catalog of tools from which you can choose if you see tools that are useful for your workload, for your way of working. So the first thing I would like to remind you is that even though I'm sure you know all about files, file is not the only way you can store data on a system. You can also use object stores or databases, and databases come in two flavors. The relational database management system that look like this in a way, and the no SQL or not SQL type of databases. I will show you some example afterwards. The main point here is to show you that you are certainly accustomed to using file systems and storing your data in files, but it's not the only way. And we will see that there are advantages of using the other part. But first, a little reminder about the file systems. So a file system is a technology that is used by the operating system to organize and store files on the system. At the very early days of computing, there were no file system at all. They were called generation 0, so the data was put randomly on the medium, and it was the job of the operating system to try to think about the data and understand what it is and try to organize it. All the way up to generation 5, which is the file system that we are using right now, such as ZFS, ButterFS, or SFS. These are more modern and they offer quite a few advantages compared to the early generations of file systems. These file systems are said to be local, meaning that they are installed on a disk in a computer and can only be accessed through that computer. There are other types of file system, like network file systems, two types mainly, network file system and storage networks, where the idea is that the disks are connected to a server and the server offers access to the disk through the network. So that's what it's called, the network file system. This is another type of technology where the network here is not a regular network that you can think of when you connect two computers together, but these are meant to store, to pass disk information rather than network information. In this situation, you had one server offering the data and multiple servers being able to access the data. You can also have multiple servers offering the data to multiple consumers. These are called parallel file system, and you might have heard already about cluster, GPFS, BFS, clusterFS. The typical usage of the cluster is for global scratch.
For the training of data management?
Yes. Another type of file system is in-memory file system. So this is a way to store a file in memory as if it were stored on disk. The advantage is that it's much faster than on disk. The disadvantage is that as soon as you plug off the computer, the data disappears. But it has its use. If you look at Lemaitre 3, for instance, there are multiple file systems installed on the Lemaitre 3. We have a large Scratch file system, which is a BGFS file system. So we have multiple servers that offer the same amount, same storage to all the compute nodes. We have a NFS server, actually a pair of NFS servers that offers a home file system to all the compute nodes. On the management node, we have an XFS file system, which is also available on the compute node. So every compute node has a local file system. It's an XFS file system. And so the whole solution of the cluster is building upon multiple types of file system. And actually, it's very important that you understand which file system to use in which case. And that will be actually the whole topic of next session. The file systems On a cluster, you can see with the df command, df like this. There are some parameters here to make it a bit easy on the eyes. But what you see is basically one line per file system. The last column is where on the local hierarchy of files the file system is, we say, mounted. So the files that are offered by the file system are available in the /scratch directory functions for the files that are on the global scratch. Here in the column, you see the type of file system. So we recognize NFS, X4, it's local file system, or BGFS, the global scratch. So all these file systems that are available in the cluster are actually mounted in different points in the hierarchy of parameters. Without the difference between both here is the I, which is absent here and present here. And you see that without the I, it shows you the volume available on the file system, which is the size of the files that you can store there, the total size of files that you can store on the file system. With the I option here, you see that it talks about inodes. And basically, inodes are the internal structure in which the data are, or the files are organized. And on most of file systems, there's a limit on the total number of inodes that you can store. And basically, when you create a file, you consume an inode. So you see it's important for some applications. So I said it's quite important to understand which file system to use for which application or which file you want to store. So if you draw a graph here with the file size, large files, and here the rate of change, so which is related to the IOPS number of operations you will do on the file, you might want to choose a file system based on those properties. So typically, if you have a lot of changes on a small file, it's very advantageous to work on in-memory file system. On the other end of the spectrum, if you have a very large file that do not move that much, you'd better use mass storage or global scratch like BGFS. But again, this will be actually the topic of the next session, and Ariel will discuss that at length. I would like now to speak a bit about the file formats. So they are a standard way of organizing the information inside a file. And I'm sure you know all about these types of file formats, which are text file formats where the information or the data is written in a human readable way. You see here JSON, which looks like this, YAML that looks like this, the INI that looks like this. If you attended the session about scripting, you remember that we use an INI library to read files and write files that were in that format, or XML. All of these are often used types of file formats to store data. And of course, I'm sure you know the most is the CSV, so the comma separated value, where the data is stored in lines where the columns are separated by commas. There are other variants with the tabs or semicolons and so on. Even though this file format may seem a bit easy to produce or read, it's very important to actually use the correct tools to produce them or to read them. So rather than writing by yourself the code that will read and parse this file format, it's important to use the library that is available in all the languages to read them, or to use tools. And here I list some tools that you can use to manipulate CSV files or JSON files. So for instance, Miller is a nice little command line tool that allows you to manipulate the data in a CSV file without having to either use Vim or import it in Excel. Here, FX also is a nice tool for JSON file format. These are text file formats, meaning that when you display the file in the command line, you actually see what's in there. But it's also important to use binary file formats when necessary. One of the most used in scientific context is HDF. So it's a file format where inside a single file, you can actually store multiple data and multiple types of data along with metadata that explain the origin of the data or what you can do with the data. Most languages that are used in scientific computing have libraries that allow you to read and write such files. And here is an example in Fortran in C on how you do that. Most important thing is you use a library that is designed to write and read those files, and then it's really much like a regular file reading and writing operation. You first need to open the file. There are some parameters that you need to specify about the features in the file, and then you have some matrix that is created here, and you can dump the matrix inside the file. And you don't need to think about organizing the data inside the file. It's all done for you by the library. What you know is that if you wrote the data with the library, you can read the data with the same library. It could be in another language or on the computer. Everything that needs to be specified in terms of byte ordering and precision and so on will be stored inside the file, and you don't have to worry about it. This is to show you that you can use libraries to manipulate those files, but you can also use command line operations. Here you see that I have two files, one with 10 values and one with information metadata about these values, and I can put both of them into a single HDF file with the H5 import. So you don't need to write the code to create the file. If you have data in some format, you can produce the metadata that will help create the file, and then use H5 import. And then you can use H5 to actually look at what is inside the file. HDF is one of the most used file formats. There's another file format which is more and more used at the moment. It's called ASDF, and it's a mix between binary and text. And actually all the metadata is pure text, but all the data is stored in binary. The advantage is that when you cat or head the first part of the file, you can read directly the type of data that is in the file. You don't need to dump it or to open to run a program to see what's inside. You can already understand what is in the file just by using the regular text-based Linux command. But then for performance reasons, the actual data is not stored as text, but in a binary form. So the same question here applies with file system: is which file format to use for which type of data. And so the recommendation here would be that for any configuration file or file with a few number of numbers or text, INI and YAML are nice because they are easy for the humans to read and to produce. It's very easy to produce a YAML file by hand. For results, with which you would like to add some context information, JSON is nice because JSON is much more specified than YAML. So the libraries that read and write JSON are less prone to errors compared to YAML. But it's a bit less easy to write JSON file by hand because it was not meant to be written or produced by hand. So whenever you have intermediate files that need to be produced by some application and consumed by some other, JSON is probably a nice way to go. For data, when it's small data, it's always nice to play with CSV because, as I said earlier, you just can modify it with any text editor you like. When the data grows large, it's always nice to try to compress the CSV. Because it contains textual information, it's actually very efficient to compress. And there are tools that allow you to manipulate or look into compressed files without the need to first decompress them. For instance, if you have a zip file with Vim, you can open the zip file and browse inside it and see what's the content of the zip file without the need to first compress the data. When the data becomes larger, a binary file format must be used. Otherwise, you will spend more time trying to read and write the data than actually performing computations with the files. And when you have really huge data, petabytes or a bit less, then you might want to move to another paradigm, not use files anymore, but try to play with object stores and databases. I would like then to point out some problems that we can that can arise with files, and one of the most common problems we as a sysadmin face is the ZOT file problem, the zillion of tiny files problem. When you store a large amount of very small file in the file system, you put a lot of burden on the file system. The reason is that it overconsumes the resources. As I said earlier, the inodes is not infinite. The inode number is not infinite. As soon as you create a file, you consume an inode. And also, the other thing is that the minimum chunk size is often large on the HPC file system, meaning that even if you write a file with only 10 or 20 bytes of data in it, on the disk it will consume 4 kilobytes, or even more, depending on how the file system is created. So actually creating a large amount of small files could end up using much more size, much more volume than what was intended in the beginning. The whole system also becomes smaller if you have a large number of small files. You enter a directory with a very large number of files, you type ls, and you will see it could take a few seconds or even minutes before you see the whole list, especially if you ask ls-l to see all the metadata. Removing files also takes a very, very long time. If you are familiar with Limited 3, you know that most years we clean all the scratch. And that operation of cleaning the scratch, because there are so many small files, often takes multiple days. So at the beginning of the week of the maintenance, we run the rm-rf command in parallel on multiple streams, try to make it as fast as possible, and often it's not finished by the end of the third day. So what you can do as an alternative is use a tar archive. So when you have a large amount of small files, it's always a nice idea, at least for storing them, to put them all in a single file. And the typical way to do that on Linux is with the tar file. Of course, you can compress it if the data is not compressed already, but already archiving all the small files into a large file that we consume 1 or maybe 2 or 3 inodes, not much. It's much more efficient. Another option, which is more modern, is to use singularity containers. So if you attended the session about singularity, you know that actually singularity are large files in which you have a lot of small files. So it sounds like a tar archive. And you actually can use the file system in singularity to store a large number of small files into a larger file. The nice thing about singularity and containers in general is that the file system that they are based on is called squashfs, and you can actually stack file systems. So you can have a singularity image with your program in it, and another singularity image, or actually part of an image, with your data in it, and you can group them together at some point to perform the computation using the software from one image and the data from another image. When you have your data in a single archive, it becomes much more easy to manipulate, to copy, to backup, or to transfer from one computer to another, or from one file system to another. Little tip here, I said we use rm.rf to remove files. Actually, we don't, because the fastest way to clean up a directory is actually to use the rc command with the --delete option and to synchronize an empty directory onto the directory that you want to empty. If there are additional chairs there if you want, or okay, perfect. So it's a bit counterintuitive because rsync is not used. What's not meant to do that, but it's a little trick. When you have a large number of small files to write, and you don't have the choice because you didn't write the software. It's always important to choose correctly the file system, as I said earlier. So try to use local file system as much as possible, or even in-memory file systems. So try to create the colony of small files in the memory file system. So typically on a Linux system, it's in /dev/shm. This is a temporary storage space that you can use that actually simply uses memory and not the disk. So you can create all your files in there and then use a tar command to create a file and store the file on your home file system or in the global file system, the scratch. But when you create them, it's always important to either create them on a disk locally or even in memory. Another option is to write all the small elements to the same file. But this could lead to some issues because of the locking. You'll realize that when two processes want to write to the same file, they need to synchronize themselves not to erase what the other has just written. And it's even more problematic when the processes run on distinct computers. And in that case, the object store or a database is a better way to go. And I would like to show you some example of that. This is an extract from the FAQ from the NFS file system talking about locking. So locking is a mechanism by which a process can tell the other processes that it's currently writing to a file and it doesn't want you to overwrite what has been written. And it says that it's broken in NFS, and I'd like to show you a small example here. The slide is a bit old. You see HMM is a cluster that we had here about 10 years ago. But basically, it's always long, so you understand what happened. I create an allocation and I request 4 nodes. So I'm given an allocation on 4 nodes, and then I run this command. And what it does is writes numbers to a single file or test file in the root directory. So with the sprint command, I run this same command on all the nodes. And so basically what will happen is that 4 nodes will write numbers in the same file. And so what we expect is first a single number, which will be 0 to 3, the processor ID, and then the number that is written, and the number is from 0. That large number. So what we expect is something like this: single number and then a 6-figure number. And that is what happens at the beginning of the file. But if I look inside the file, I can find this kind of pattern emerging, which clearly are because 2 processes have been writing at the same time on the same line on the file, because they were not able to lock the file properly and say, okay, I'm writing, don't write over this. And you see it's complete sense here. So the take-home message is, do not rely on the file locking mechanism of NFS or BGFS or whatever. And trust that if you write to the same file from multiple distant computers, it will go nicely. It could go nicely, but you could also end up with something like that. Any questions about those? About the whole file ecosystem? No. Then we'll move on to object storage. So object storage is a technology that manages to do that as objects alongside with a variable amount of metadata. So I've been talking about metadata when we were talking about files. The metadata associated with files are the owner, the date of creation, the permissions. Here, the set of metadata is not defined, and you can choose the metadata that you associate with the files that you store. And it offers also a globally unique identifier, which makes it easy to share on other systems than the one on which they reside. Maybe you've heard about these technologies, so Swift, S3, or Ceph. they have nice properties from the seasoning point of view. They were first meant for web applications, but actually we can see them more and more arriving in the scientific context. And they allow accessing the data with the REST interface, not the POSIX interface. So when you read a file, you need to open the file. You have system calls to read, write, and close to save the file. Here, it will be much more like a web-based experience. If you have access to Lumi, you might know that there is an object store available on Lumi that you can, of course, it's not free, you need to pay at some point. But as I was saying, object stores are coming to HPC and then can offer benefits over Filesystems system in some cases. The way you use an object store, here is an example in Python. You use typically, as always, a library to do the job. You don't want to interact by yourself at the HTTP level with the server, but you use a library or package. You need to specify an access key and a secret key. These are the credentials that you use to access the data. And then you need to create a connection. And creating a connection is the equivalent of opening a file. You need to specify the host name or IP address and the port of the server, and then you can create buckets. And a bucket can be thought of as a directory where you will store data that are logically put. Then you can create objects in the bucket. Here are two examples from string. So here I create an object which is simply a string that says a file, or you can create an object from the content of an already existing file in the file system. What is important is that when you create an object, you need to associate a key with it. And the key will be the key to retrieving the object afterwards. You can relate to the name in the file system, the name of the file. The nice thing is that once you have uploaded your file and created a key, you can request an URL to that file, and you can actually access the file simply with a web browser. So you see, this is the name of the bucket. This is the name, the key. And when I click here in a way, then it gives me, okay, there's an hello.txt document that is available for you to download. So then the nice thing is that when you store your data in an object store, you can actually access it from possibly anywhere in the world, provided that the file was allowed. That's different from a parallel file system when you need to access with SSH the file system to retrieve the file. So you need to have an account on the file system, on the cluster. Here, you can share data with anyone without the need for them to also have an account on the cluster. A tool that is very handy to play with this is Arcloud. It can be thought of rsync, but with cloud storage. And so that includes all the object files that that I've shown earlier. The object storage that I've shown earlier. So I'm not going to show you how to use it because the way you use it is slightly different depending on where you access an S3 file system, or we can also access Dropbox or OneDrive with this file, which is a simple command line that works with rsync, but with every other type of storage and file system we can think of, basically. So when should you use an object store? First, if you have access to one, this premise is important. But basically, when you have data that is written once and read a large number of times, the object store is a nice way to store it, especially if you need to read it from multiple locations. As I said, data stored in an object store can be accessed from a larger perimeter than simply the computers that are part of the cluster needs attached to the file system. Also, if you have jobs that write multiple independent small files in parallel, as I said earlier, it's a bad use case for file system. But actually, for object stores, The nice property of object store is that they have less constraint on the level of synchronization they need to offer the user. So actually, when you write to a file system, the file system must make sure that as soon as the file is written, it can be read from any other computer that is connected to the file system. And that takes a large amount of operation, synchronization, and barriers. While on an object store, what the object store promises is simply that it eventually will be available from all computers. So the restrictions are much looser, which allows it to work faster. Any questions about object stores? No, just something that you need to keep in mind when you will have access to one eventually. You will remember here, you will take the 5 slides, have a look at pointers where you can find information to further work with it. Now I'd like to move on to database systems. So it's typically a system that interfaces users, applications, and the database itself to capture and analyze the data. Most of the database systems allow you to run operations that manipulate the data or extract statistics from the data. Here are examples. I'm sure you've heard about MySQL, for instance, or SQLite. They are mostly needed for categorical data and alphanumerical data, so not much suited for matrices. But if you have strings or categories, it's a nice way to store them. They all have the opportunity to create indices on the data, meaning that retrieving one single element in a large collection of data is very efficient with a database, compared to a file where there would be no index and you would need to parse every line of type to retrieve a specific element. Here with indices, you can directly go to the correct line and get the data. They have some theoretical properties, which I will not go about, but most importantly is they encode the relationships between data. And I'll show you just simple example here to give you a feeling of how data is organized. Data is organized in tables, let's say, where a line is called a tuple and a column is called an attribute. And here is an example where we have a login, first name, last name. And this is a table, this is another table, and you see that those two tables share a column, the login column, and that allows to create relationships between these. So we know that Mark here is the same Mark here. And so the person named Samuel Clemens has this phone number. This is what the language that you can use to connect or query a database look like. So all the databases that I've shown earlier understand the same language. You see there are commands to create tables. You see here create table user. So this one, you need to specify the types of the columns. You can insert into a table a line. You can insert a line into a table, and you can select, which means look for in a way. An example here is select first last from users where login equals line. So even if you don't know anything about SQL, I'm sure you understand what this is all about. So the nice thing about SQL, which is the name of this language, is that it can be easily understood. The other thing is that it allows to create queries that are joins, meaning that when you have two tables with a key between them, so a common column, if you want, the join operation will allow you to get a single table with as many lines as the union of as many columns as there are in the union of both tables. One of the drawbacks of the systems is that you need a full server dedicated to that, except if you look at SQLite or DuckDB. These are two programs in a way that allows you to have the same feature as a complete relational database, but simply based on files. So when you're on a cluster and you say, okay, I would like to store my data in the database, but the sysadmin, they don't want to add another server and install a SQL server or MySQL. So then you can say, okay, not an issue. I will install. I will use SQLite, which is basically used through the language that you are using to use. So if you're using Python, there are libraries to use SQLite in Python. If you're using R or Tron, there are all libraries to use SQLite. And then when you have installed the library, you can, in your code, use the same SQL commands that you would use against a real database, except that behind the scenes, it's a single file that you will be able to store on your file system or the cluster. And then I think is that if you have a large number of small elements, you can store them all in this file, which solves the problem that we mentioned earlier about the large number of items. And also, thanks to the index, it allows you to find the information that you want very quickly and easily. This type of file system, this type of database is very old. And nowadays you will encounter more and more the more modern types of databases, which are called NoSQL databases. And you see that they have a different set of theoretical properties. And they are more tuned to certain types of data. For instance, key value stores are really designed to store a large number of independent collections of data that are not part of the same region, so not part of the same vector functions. Graph databases are specifically designed to store graphs, so connected edges. Column databases are designed to store matrices. I said earlier that a matrix is typically not the kind of data you want to store in a relational database, but with those kind of databases, they are really designed to work with matrices or kind of things. And the document type, they store basically JSON objects. Just like with the MySQL server, you need a server to actually run the program that offers you this type of services, except if you use something like TinyDB, which just like SQLite allows you to have the properties of a relational database management system on a file. Here with TinyDB, you have the same feature as MongoDB, which is the document database, except that rather than having a full-blown server that offers it, you simply store it in a file. And again, the way you use it is using a package or library that is already provided by the people who wrote TinyDB. And then you can run the same commands as you would do against a MongoDB, except that here it goes to a file. So when would you need to use that kind of storage system? The real good use case is when you have a large number of small files. I've said it's not meant for the file system, but it's very nice for a MongoDB database, for instance, when you have a large number of small pieces of information. Also, when you do a lot of direct writes in a large file, it's very heavy on the file system, very on the I/O. You will find that it will be faster to use a database. Of course, when the data has hidden relationships, has clear relationships between them, and you can encode that in a relational database system, you should use that. Also, the nice thing about databases compared to files is the assurance about the integrity of data is higher than on file systems. So files offer some degree of protection against crashes with the logs and so on. But the databases are, most of them, actually all of them, make sure that whenever you write data, it cannot be corrupted by a power cut or some other hazard. And when you have files that need to be updated by multiple processes, I've shown earlier that could be an issue. It will never be an issue if you use a database system. The converse is when not to use such technology. When you are only reading large files from beginning to end, it will always be more efficient to have the data in a file than in a database or in an object store. When you have simple vectors or matrices, the CSV file is often most easy to work with system. And also when you have the need for direct access to files, fixed size data structures in a file, it might be easier to use a library such as a GA file and so on, rather than storing in a system like this. Do you have any questions about this? Again, it's a bit abstract at the moment, maybe, but my hope is that when you will encounter a situation where you think or you feel that the file system is failing you, you will think about this and go look for the tools that I've shown in the slides. So now I would like to move on to data transfer. How do we transfer data from one computer to another computer? Basically, I'm sure you know about SCP. This is the simplest way to copy data from two Linux computer. The way it works is SCP, some file, and some destination. Destination can be removed or the source can be removed. The thing is that it's not very efficient. The reason is it's working in a serial stream, and it's much synchronous, meaning that the protocol that is hidden behind the SCP always keep asking the destination, did you receive the data? Did you receive the data? Did you receive the data? And when it does that, it does not transmit the data. So actually, it's a very inefficient protocol. Another popular option, which is a bit better, is rsync. So why is rsync better? It's because rsync first try to minimize the amount of data that must be transferred based on what has already been transferred. The way it's used is exactly like SCP, with rsync, then the source and the destination. Both the source and the destination can be removed. There are two arguments that you should always use: is -a and -z. Otherwise, rsync does very basic stuff and does not remember the metadata and so on. Does not also crawl through the internet. Here are optional arguments that you might find interesting. -v gives you verbose output. --progress gives you additionally the progress for single files. --include or exclude allow you to exclude files from the synchronization or to only choose a specific type of file. When you want to move data, you need to use -delete or remove source files. They both indicate that you should remove files. The -delete will remove file from the destination that are not in the source, and --remove source file will remove the source file when it's then moved to the type. --dry run is a very nice option that allows you to see in conjunction with -v what rsync would do, but will not do it. It's always important, especially if you are using the descriptive parameters, make sure that you do not make a mistake. And then here are some options to make it go faster by skipping some checks at the beginning. So rsync can be used to resume transfers. If you have been using SCP a lot on large file to systems that are far away, I'm sure you have encountered the problem at some point that the connection was closed or shut down, and you end up with a half file or a portion of the file already copied, but not the entire file. If you use SCP, you have no other option than trying to transfer again the whole file. If you use rsync and use the --append parameter, you can actually tell rsync to continue exactly where it was interrupted. So here you see an example where I use SCP to copy a file from one computer to another, and then I use rsync to copy the same file. It takes some time. And then I do SCP and I interrupt it, and I use this time --append, and it goes much faster simply because it did not recopy all the file, just a portion that was not copied there already. Another thing that you might keep in mind is, again, I'm talking about large number of small files and how they are a problem for file systems. What people do often is use star to, on the fly, create a single file with all the file that you have in the file system, and then SSH and use pipe to create the file on another file system, on another computer. So if you are on computer A in a directory with a large number of files, you're trying to do rsync, and then rsync takes forever just to list all the files. What you can do is create, okay, I'm gonna create a table and copy it in this single operation without the need to have the space on the source directory to create a table itself. Simply it will go through the network with the pipe SSH to the destination in a single file. So the nice thing is that on the destination, you have already a single archive where you don't need to pack all the files into a single file. You can work the other way around with this by SSHing to a remote server running tar there and writing the file locally. This avoids a lot of communication overhead between the computers that would be needed by the synchronization of the metadata, because it's all encompassed into the file. Also, you can use the PV command, which is pipe viewer. When you have a pipe like this, you put pipe PV pipe, and it gives you a progress bar of the transfer and the rate of the transfer if it's not able to predict the size of the transfer. Any question about this way of working? No, it's just playing with a regular Linux command. If you remember, most of the sessions here are about going parallel because the clusters, they are meant to run parallel computations. And actually, you can also run parallel transfers. I said earlier that SCP was inefficient in its protocol, and there are tools that allows you to actually run multiple streams between the same computer. And the effect of that is to maximize the usage of the bandwidth available of the network. And so BBCP is a tool that you can install by yourself on clusters, and you can specify the number of processes or number of streams that you will use to try to maximize the use of the available bandwidth. And so here you see an example where I first copy a file from one computer to another using SCP, and then I do the same with BBCP and 2 streams. And you see that it's been faster. Of course, here the file is small, but when you have a large file that takes 10 hours to copy, but it could be a bit less with such a tool. The drawback is that you need the firewalls to be friendly in both directions for the computers you are synchronizing data between. So it will not work between 2 clusters from 2 different universities, but it could work from 2 clusters from the same university, or from a cluster to a storage system, mass storage, or so on. You can also use rsync in parallel. And if you attended the session about parallel computing, I've been showing you the GNU parallel command. I show you how you can run computations in parallel with GNU parallel. Actually, you can run also rsync in parallel with GNU parallel. So this except is taken directly from the documentation from GNU parallel. And so there's a recipe here to run rsync in parallel. And so the parallelization would be over the streams and also over the file enumeration. So if you think that your rsync is taking too much time, you can try to sneak in the GNU parallel. There are tools that are available that try to package GNU parallel and rsync in a single option. There is parsync FP, which is also based on a program that tries to maximize the speed at which files are discovered on the file system, and FP sync, which is basically the same IDs implemented in other ways. So you can try to see if either of those are good fit for your needs. Do you have any questions about this? No, some counterintuitive ideas on how to transfer files from computers to computers, but sometimes they can make it much faster than simply using the C. So now I would like to talk a bit about data sharing. And first, with other users on the same computer. So often you have data that you need to share with other people from your lab or from your team. And one of the ways to do that is, of course, with Unix permissions. I'm sure at some point you're familiar with Unix permission. This is a single summary where for a given file, you have a user, a group owner, and then a set of 3 permissions, and the one applies to the user. The first one applies to the user, second one applies to the group, and the third one applies to all the others. And the permissions can be read, write, or execute. Actually, for directory, the action can be thought of as traverse. Go through. And with that, what you can do is actually share files with a specific group. So here, what I'm showing you is the use of the G permission, which is not one of the base permission, is one of the extended permissions here. And what it does, it tells the system that whenever a file is created in a directory which has such G bit set, the files that are created them must be associated to the group ownership of the directory, of the parent directory, and not of the file. So let me show you an example here. So I'm creating a directory that's here. I am part of a group, which is this group, which is not my main group. But it's here. Here's my main group, so grp. So when I create a directory, the group ownership of the directory is grp. If I want to share this directory with people who are part of another group, for instance, here, grp-rcv, what happens is I can use a chgrp command to change group, so to change the group ownership of the file, so that of the directory, so that when people from that group want to try to access this directory, they can do it, provided that the group permissions here are set correctly. So here with R and X, they would be able to see inside the directory. The problem, if I don't do anything further, is that when I create a file, you see the default group ownership of the file is my primary group, which is not something I want if the intent is to share all the files that are in this group, in this directory. So if I set this bit in the permissions on the directory, whenever I create another file here, you see that the group ownership of the second file has been set to the group ownership of the current directory. Okay, so when you have a directory in your home file system or in the global Scratch and you want to share it with people from another group, it's always a good idea to set up this GSUD bit on the directory so that whenever you create a file there, you don't need to think about it. If it's created in the shared directory, it will be shared with the other people of that group. If you don't have a common group between you and the people you want to share the files with, you can use a trick like this, which is to actually allow traversal on a directory, but not read. So you see here, there's no R and there's an X here, meaning that everyone on the computer can actually look through the directory, but not list the contents. So if you are not part of this group or you are not me, you will not be able to go in my home directory. But if I give you the name of a file in the directory, you will be able to read it. So here you see on the right some other people. They cannot look at what's inside my directory, but given the fact that here there's an X permission set for everybody and an R permission set for everybody on this file, they can look at the content of the file in my home directory, even though they do not have access to my home directory. So this is a tip that is often used when you need to share data with some other people and you don't have a common group to which you can assign the file to share them. Do you understand how this works? So this is often very much faster than asking the system admins to create a group just for you to copy files or share files. You can always ask for the creation of a group to share files, but in the meantime, before the group is created, you can play with things like that to share the files. Another option is to share encrypted files, and it's very easy on a Unix system to encrypt a file with OpenSSL, which is installed virtually everywhere on these Linux machines. Basically, when you have a file, you can run something like this. It requests a password, and then it produces an encrypted version. And if you look at the contents of the file, you cannot interpret it at all. But if you give this compressed file, or if we make this compressed file, so this encrypted file readable for the whole world on the system, and you share the password with only a small group of people, then it's a way to share the data with a small group of people. When you want to decrypt, you run the same command with a -d here. It requests the password, and then you get access to the clear version of it. So it's very easy to encrypt and decrypt files on a Linux file system, and it's a way to share data with a specific person without the need for additional structure or additional configuration from the admin part. Any question about that? There are other ways to encrypt the data with GPG and so on, which are based on symmetric keys, much like SSH, for instance. But this is a symmetric key, is very easy to associate a password to a file, and you share the password in the file. One thing I can mention furthermore is that if you are used to using Vim, in Vim, you know that you can save and quit with the :WQ. It's similar to :X, which is a shorter version. And actually, if you write :X with a capital X, it will ask for a password and encrypt the file that you want to save. So it's an easy way to encrypt the file. If you don't want to remember this, you can just use Vim and use :X, and it will encrypt the file on disk. If you use Vim to read the file, it will first ask the password, and then it will show you the file. So now this playing with the groups assumes that the people you want to share the data or the files with all have access to the same cluster or the same machine. Here, I would like to show you some tools when it's not the case. So, for instance, you are starting collaboration with people from another university or in another country, and they don't have access to the master system here. They need to have access to a file. What you can do is play with the tools that we have. It's called Nextcloud. So actually, I will show you examples here with the Filesystems instance of Nextcloud. But there is a Nextcloud instance in most other universities. The name sometimes is a bit different because they brand it in some way, but basically the same software hidden behind. This is in Namur, this is in ULB, this is in Liège, I think. Yes. So look in your university, you most probably have access to a Nextcloud instance that will allow you to do things that I will show you here. So here I'm connected to the Nextcloud interface in the Filesystems here. What you see is it looks a lot like a Dropbox or use that. The thing that is nice about Nextcloud is that it has what they call as FTP connectors that allow you to connect the Nextcloud instance to a cluster, for instance. And here you see that I have three connectors, 1, 2, green, 1 back. These are clusters that we used to have here, that we see here, and to the storage, which is the main entry point for the mass storage here in the silver. The nice thing is that when I do that, actually the content of the files that are connected to with these configurations appear here as if they were stored in the Dropbox, meaning that you can also share them using the sharing options of Dropbox. I'm saying Dropbox all the time, so of Nextcloud, of course. So here, what you see is that I am sharing a file that comes from one of the connectors, and I create a share link, which I can then share with some other people from some other universities. When they click on it, they arrive at the page where they can download the file. So even though the file itself is stored on an NFS server, which cannot be accessed from outside the university network, you can share files that are on it using Nextcloud and the SFTP connector. Okay. Another tool which we have installed recently is Dataverse. So this is a data storage system that is meant to publish data. So I'm sure you are familiar with the idea of publishing papers, and most of the time, if you are here, it means that your research is based on data. And if you want to share data alongside with your paper, you have multiple options, like putting them on a web server somewhere and having the URL of the web server in the paper. Another option is to register to a system such as this one, that will furthermore offer you a DOI for your data. So a single identifier for your data that will be then published as your papers are published. And you can refer papers in the data storage, in the data store, and refer to data in the paper simply by showing the document identifier. So here is what it looks like. This is for UCL1, but there are the same systems again in all the other universities, and there are works undergoing to actually try to federate all such systems from Federation World and Brussels into a single entry point of all data sets. So basically what it looks like, if you have data, you can upload it and you see when you don't see it, but basically this is the DOI of the data set. So it's a single identifier for the data. The thing is that once the data is published, it's you cannot modify it anymore. It's really frozen in time. And if you want to, you can of course upload different versions of the data sets, but they will then be identified as versions of the same data. But once a data set is published, it's like a paper. You cannot just go on the website and modify some numbers in the paper, but you can publish an errata, something like that. The first session of the afternoon will talk a bit more about all this idea of open data and open science. So this is about everything I wanted to say about the data. So again, it was not a comprehensive tutorial with some tools, but rather some ideas, and try to help you to find the right file system for the right file format for the data that you are storing. Trying to make you use parallel tools to transfer data, either BBCP or parallel tools based on rsync. And then I've shown you some basic tips and tricks on how to share data between users on the same system or between users that are not part of the same system.